coming. Let's dive in. My talk is deeply declarative data pipelines. Let's dive in. Looks like we're ready to go. All right. So first off, what are data pipelines, right? So data pipelines basically are things that transfer data from sources to sinks, like between databases, that sort of thing. Data pipelines can involve replication with something like Mirror Maker. They can include filtering, joining, routing, message transformations with things like Flink. They can involve streaming ETL or reverse ETL with things like Kafka Connect or Goblin or any number of other systems. You can also group change data capture under this umbrella. Things like the Debezium project and Brooklyn involve CDC, change data capture. And also data pipelines generally include batch, but for this talk we'll focus on streaming. This is a very large domain, so we got to focus it somehow. Right, so what's in a name, right? What do I mean by deeply declarative, right? So if you think about like computing things in general, right? Languages, APIs, that sort of thing. They tend to sort of fall on this sort of continuum, this sort of spectrum, right? Of imperative versus declarative, right? And of course, this is a gross oversimplification and not all things are easily classified, but that's sort of like, you know, the metaphor we're using for today, right? So things over on the imperative side, they tend to be explicit, concrete, and imperative. And they also sort of tend to be general purpose. Things like assembly is extremely general purpose. They also tend to be internally simple. Again, assembly is pretty simple and like there's not much to it. But it ends up being hard to use, right? On the other end of the spectrum, right, things that tend to be declarative, they have a lot more implicit context surrounding them because they tend to be more domain specific. And that means that they end up being more internally complicated, but easier to use. That's sort of like the whole point, right? So if we're trying to make data pipelines as easy as possible, my thesis is like, let's try to push them further and further towards the declarative side of the story and see what happens. So that's sort of the gist of the talk. All right, so I recently heard a really great metaphor from Julian Hyde. He said, you know, when you call up a pizza place to order pizza, you don't walk them through a set of instructions that ultimately result in the pizza you want, right? You sort of like describe the attributes of the pizza, right? You say, I want, you know, pepperoni, large, extra cheese, whatever. And, you know, it's sort of hard to imagine if we couldn't do that, right? So that's sort of like the, you know, obviously one way is declarative. You just say, I would like a, you know, a large pepperoni with cheese. And the other way is imperative. You're sort of like walking through the pizza maker how to make pizza, right? Which maybe you lose some control, right, in the declarative approach. Like maybe you really want it to be at 451 degrees, right? But it's hard to imagine that and making that trade-off. Another interesting thing is like you don't even have to use the word pizza, right? When you order a pizza, you don't have to even say pizza because there's so much like context that's implicit in that phone call, right? So that's what we're trying to accomplish with data pipelines. Like how implicit can we get? How declarative can we get? All right, so when do we need data pipelines? I think, you know, in present company, right, this might be interesting, right? We might have databases of different types with different performance characteristics, different capabilities, and we need to move data between them, right? Maybe you have like MySQL over here and you have Pinot over there or whatever. So that's when data pipelines tend to come up. So one way to tackle data pipelines is to use Kafka Connect. This is sort of a sub-project of the Apache Kafka project. And Kafka Connect sort of approaches data pipelines as connectors. So when you talk about data pipelines, you tend to experience connectors. It comes up a lot. And Kafka Connect being, you know, part of Kafka, it leans heavily on Kafka, right? So you can have like a connector that pulls data from MySQL, pumps it into Kafka. That's a source connector. And you can also have sync connectors that do like ETL-y-like things, which might consume from Kafka and like dump into HDFS and that sort of thing. So using Kafka Connect, you can build pipelines that move data around leveraging Kafka. So connectors are nice because they're already fairly declarative in the sense that you don't have to really write much code to use them. If the connector already exists, someone's already done the work of creating the Java for you or writing the Java for you, you really just have to configure your connector. So here's some example of what what configuring a connector might look like, right? You have to tell the connector, what port to reach, what username to use, and so on. But that's mostly it. Kafka Connect also understands this concept of transformation in the middle of pipelines, right? In Kafka Connect, there's something called an SMT, a simple message transformation or transform. And by configuring SMTs as part of your pipeline, you can do you can do routing, you can do flattening, you can do filtering, that sort of thing. So you can actually do some measure of computation. It's not just moving data; it could also be some measure of processing. And these transformations are also expressed just in configuration. So SMTs in Kafka Connect are also sort of like intrinsically declarative, right? That if someone's already implemented the Java code to implement filter, you just have to configure it to point it at your data. Right. So this means that the sort of experience of using Kafka Connect to build data pipelines tends to be very configuration driven. You basically write some JSON for one side, maybe JSON for the other side. Maybe your job is just from MySQL to Kafka and someone else writes the next step. But it's basically writing configuration. So it's already pretty declarative. I think this tends to break down when your data pipelines get more complicated, though. Maybe we have a join that we want to accomplish in the middle of our pipeline, right? Maybe we have a change stream from some operational database, and we also have an event stream from something like Kafka, and we want to join that and do some sort of lookup or something like that. So in the Apache Kafka ecosystem, the answer to this is Kafka Streams. Kafka Streams does stream processing on Kafka topics, right? So you kind of have this this sprawling architecture of databases, connectors, SMTs, Kafka Streams applications, which basically just touch Kafka, and then that's how you can construct these data pipelines, right, to do whatever you're trying to accomplish. And if you're using Pinot, incidentally, your Kafka Streams app can just output Kafka, and Pinot will ingest Kafka. But if you're using something not quite so friendly to Kafka, you may have other connectors downstream, right, to load into some other database, for example, right? So I'll compare that with Apache Flink. Apache Flink is interesting because it's interesting for a number of reasons, but it tries to accomplish all of that within the scope of a single Flink job. So the connectors and the stream processing are sort of smashed together into one thing. So I think that's a more powerful model. But it's also intrinsically less declarative because you're writing Java code and writing jobs and stuff like that, which is not just a configuration-driven experience. So what I want to do is take the power of Flink and make it more declarative, right? And let's see what happens. All right, I want to stop for a second, just point out. I think it's kind of interesting, but data pipelines can do really interesting, business-critical, important stuff, right? It's not just moving data between databases. You can have you could have a Flink job, for example, that's joining an ad click stream with some new account CDC stream and figuring out who do we charge, how much do we charge, emitting money stuff to Pinot and that sort of thing, right? So we could potentially build business critical things just within the scope of data pipelines, right? So it's not just about moving data, it can be your whole business, which is pretty interesting. And also, notice there's no microservices, there's no REST APIs. We're just writing Flink jobs, which is potentially really powerful. All right, so hopefully I've sold data pipelines to you. How do we make them easy, right? And I'll sort of narrow the scope of that question to how can we build new data pipelines with as little one-off code as possible, right? What I'm going to show you is a lot of upfront work, right? But once we do it, once we build out this sort of machinery at our organizations or whatever, building Flink Job 2, building Flink Job 3, and so on become very easy. All right, so let's dive in a little bit to Flink. If you have experience with Flink already, you probably are used to thinking of Apache Flink as a stream processing framework. So let's look at what stream processing looks like in the context of Flink. So one way to write stream processing jobs with Flink is to use the data stream API. So I don't want to walk through this code or anything, but I just want to point out that it's already fairly declarative. It's in Java, but you see joins, you see filters, you see windows. We're not writing for loops here, right? You're not exactly walking Flink through the process, right? It's already fairly declarative. It's just in Java, and it's maybe not configuration. That sort of changes. Relatively recently, Flink introduced the table API, and the table API actually does have a lot of configuration. And the interesting thing about the table API is it introduces connectors as sort of like a first-class element of Flink. So you see here, this is Java code in a Flink job, and it's instantiating a connector. And I highlighted here, you see Debezium. I think I mentioned Debezium earlier. It's a Kafka Connect-based project. So it's kind of interesting because someone took the Kafka connectors and sort of ported it over to Flink. It's sort of like shows or illustrative of the fact that it's sort of like pulling connectors into the same place, same job, instead of like the sprawling architecture of different things connected together. All right, so the rest of the code looks there's a lot of like configuration, but it looks very similar to the JSON that we wrote earlier, right? And then down at the bottom, we see our where, we can have our filters, we can have joins and that sort of thing. But you notice the code is now like the stream processing aspect is dealing with just tables. So I guess that's why they call it the table API. It sort of expresses everything as a table. And this warrants some explanation because a table in the Flink table API is basically a connector. Like there's physical tables in some other database somewhere. Flink doesn't necessarily touch those tables directly, but it talks to those physical tables through connectors. So when we're talking about tables in Flink, we're not actually talking about like the physical table in some physical database, but we're talking about a connector abstracting over that physical table more or less. All right, so the Flink table API sort of exists to power Flink SQL. So the Flink SQL API, basically you can think about it as two different types of statement. Hopefully some of this is familiar to you if you've ever touched SQL. But you have like data definition language, which sort of like defines what a table is, what tables there are, what columns they have. And as you see, it calls out, or I'll call out if I can get my thing to work here. You see connect, no, it's not gonna work. You see connector in the configuration, right? So again, this table is like the statement create table. It's not actually going to create a table in like a MySQL database, for example. You're really declaring a connector with appropriate configuration to point to some physical table. And I think that warrants a call out because like create table is not really what it's doing. It's really just configuring a connector. But once you get that out of the way, now you can use all those tables that you've created using DDL to query those tables using very familiar SQL, right? So select star from inventory where op doesn't equal D. That should make sense to almost everyone, right? All right, so why are we getting into Flink SQL? Well, I think Flink SQL is extremely interesting within the context of data pipelines because all of that like sprawling stuff that I showed before, you can sort of like just describe it in one line of Flink SQL, right? Like if you write insert into stock, select star from inventory, and so on, you have a sink, you have a source, you have some transformation. So all of these things are present just in one line, right? So this is powerful, right? But there was a lot of work to get to this line, right? All right, and if you sort of winced when I mentioned Flink SQL or SQL in general, this might be why, right? Like the experience of using SQL within some other host language like Java isn't that fun, right? So Flink SQL sort of suffers from this because you have to eventually write a Flink job, which is a Java application, it's a jar, and you might have Flink SQL inside there, to do things like, create table and do your selects and that sort of thing if you want, but it's not that great of an experience, and it's declarative, but it doesn't, for some reason, it doesn't feel very gratifying, right? All right, so once you build such a Java application, maybe you're using the table API, maybe you're using Flink SQL, how do you actually go about, deploying such a thing? If you sort of winced when I mentioned Flink, one reason might be that you have this like older model of I need to carry around a Flink cluster. I have to deploy a Flink cluster. I have to own a Flink cluster. Well, this is also relatively new. The Flink project now includes a Kubernetes operator, which is really interesting because it means that you can deploy a Flink job with basically nothing more than a jar. Like if you have a jar and you write a little bit of YAML, you can deploy that. You don't need a Flink cluster already. You really just need a Kubernetes cluster. And you can see some evidence of that. Like this is all it takes to deploy a Flink job once you have the jar, right? And you can specify like how much memory to give a job manager, but you don't have to have a job manager. The operator will go set it up for you. So what did a human need to do to deploy this Flink job, right? So you have to write some Java, you have to compile the jar, you have to store the jar somewhere, usually stick it in a Docker image or whatever. And then you can write your Flink deployment YAML, which tells the operator what to do. And then you can deploy that YAML, and the Flink Kubernetes operator steps in, processes that Flink deployment YAML, generates other things, other YAML downstream, and then eventually your Flink job is running. So that's actually pretty great. That's pretty easy. It's not very declarative, but it's pretty easy. So can we do better, right? I think we can do better than this experience. So I'll walk you through some sort of evolutions of this model, and we'll push it almost to absurdity to see how declarative we can get this model. So the first level of deeply declarative is let's stick our Flink SQL in the YAML, right? Let's stick it in the same spot as the rest of the YAML. So this involves writing a Flink SQL runner application, writing a Flink SQL job CRD, a custom resource definition, and basically writing a whole new Kubernetes operator. All right, so the idea behind the Flink SQL runner is you basically write your Java once, and it loads Flink SQL from file or from arguments or downloads it from somewhere, and then runs it, right? So you write your Java once, you compile your jar once, and then you're done with your job. This is the last Java I have for the rest of the slides. No applause? Oh, interesting. So anyway, so very simple idea. And actually, Bing auto-generated this code, so I didn't have to do anything to write it. And when I've written it by hand, it's been considerably less verbose. So there's really not much to do here. All right, so Flink SQL job custom resource. So I mentioned a CRD, a custom resource definition. So in the Kubernetes API, if you're not familiar with this concept, I'll rehash it real quick. But within the Kubernetes ecosystem, there's resources like pods and deployments and replica sets and things like that Kubernetes understands. But you can also extend the API with custom resources that represent whatever you're trying to deploy or manage. And you do that with a CRD, a custom resource definition, and almost invariably a CRD will be like implemented with an operator, which is something that understands a CRD more or less. So that's what we're going to do. We're going to write our own custom resource definition, which is basically a schema. This is an example of a custom resource that would sort of like implement our custom resource definition. I won't show the custom resource definition because it's like hundreds of lines usually. But anyway, so we'll have like a Flink SQL job. A Flink SQL job is I can deploy it and configure it in the same way I would deploy like a pod or other deployments in the Kubernetes ecosystem. Right. So and sort of the important part here is that I have the SQL for my job to run in that same file. So now I have one file. It's got like a name and some SQL, and that's pretty much it. So this is pretty declarative, right? It's pretty simple. If all I have to do is write this and deploy it, then that's a pretty good experience. So how to do this? This, like I said, this involves writing a Kubernetes operator from scratch, more or less. And the idea here is that you write something that takes the Flink SQL job custom resource YAML and turns it into YAML or resources that Kubernetes understands natively, or that some other operator understands, which then turns into things that Kubernetes understands natively. So you sort of have like this cascade of operators in really complex, and this is the direction we're going basically. So the Flink SQL job YAML, that's where your SQL is. The Flink SQL job operator picks up that Flink SQL job custom resource YAML and turns it into, let's say, two artifacts, the SQL script, which could be a native Kubernetes config map, for example. That's just something that Kubernetes understands. And then the Flink deployment, which is something that the Kubernetes operator understands, right? So this could be scary. Operators tend to be scary, but there's not really that much logic here. It's just YAML in, YAML out. And just to belabor this point, if you've never implemented an operator before, I think they get a bad rap. They have traditionally been extremely complicated to write, but for things like what we're trying to do, it's just YAML in, YAML out, and maybe you have multiple such functions. In the Kubernetes ecosystem, they're called controllers, more or less. But you basically throw YAML at Kubernetes, and the Kubernetes gives it to a controller, and then that controller generates more YAML, then it goes back to Kubernetes, and that's what an operator is. And so if you think about it as YAML in, YAML out, it's not that sophisticated. All right, so why are we talking about Kubernetes anyway, right? So the whole point of this is that once I've written my YAML to describe my Flink job, deploying that Flink job is just kubectl apply in the same way that I would create a pod or, like I said, a replica set or anything in the Kubernetes ecosystem. So I just write some file, kubectl apply, my operators take over, right? So what did a human have to do? We write some SQL in a YAML file, we deploy the YAML, and the rest of the work is done by the operators, right? Or, you get the point. All right, so that sounds pretty great, but this is still not trivial, right? The highlighted code here is actually pretty hard to write as a human. And it ends up being extremely fragile if you think about it, because like I said earlier, these create table DDL statements, they're actually describing how to connect to a physical table, but that physical table could diverge from what you have written here, right? So this is inherently fragile. Like if someone adds a column or changes the data type of some column in the MySQL table, this Flink job may suddenly not know what to do because this DDL is no longer a reflection of reality. So there's some problems here with like handwriting this DDL, even if it is SQL, right? So next evolution of the idea is let's implement table YAML. So we'll introduce a new CRD, we'll call it a Flink table, and we'll make our operator a little bit smarter. Okay, so same idea with the Flink SQL job operator or custom resource. We can have a Flink table custom resource, and the idea here is that we just stick our DDL in one spot and we give it a name, right? So we call we have user behavior, we have user items, and the point of that, right, is that it exists in one place. And then we just can reference it. We don't have to like copy and paste this around in every Flink job that might have to access this data. And that means we can modify our Flink SQL job custom resource definition to understand tables instead of DDL, right? So you can sort of imagine where this is going. But now all I have to do is write my SQL. I don't have to write any DDL. Then I just reference the tables that my SQL needs, right? So it needs user item counts, it needs user behavior. So I just reference those existing tables that someone else has already written for me, right? So this is really easy. If we've done the first step, we're getting much easier, right, to make the next SQL job. So in order to do this, we need to augment our Flink SQL job operator with this understanding of Flink tables. And the basic idea here is, right, when the Flink SQL job operator gets a Flink SQL job, it then looks to see what Flink tables are referenced in that YAML, and then goes and queries Kubernetes for those corresponding Flink tables to get their DDL, and then assembles them into a DDL plus SQL script, and that's what it hands off to the Flink SQL job operator, or the Flink deployment operator. Right, so this model sounds pretty great, but there's some problems with it. One is like, well, what happens when you delete one of these Flink tables? So generally in the Kubernetes ecosystem, when you create something, it means that you're like deploying some workload, some physical pods start running. But if I delete a Flink table, like what does that mean? Should something stop running? I'm not sure. I don't think it's clear. So something's a little fishy about this model. On the other hand, if I delete the Flink SQL job, I think it's pretty clear that that means that the Flink job should stop and get destroyed. And that sounds, like a lot of work for the operator to do, but actually it ends up being extremely simple because Kubernetes natively understands or supports this concept of an owner reference, and we'll talk a lot about this in the next couple of minutes. But an owner reference means that when a operator spits out YAML resources, it can link those resources to some owner. And the reason why you would do that is because if I delete the Flink SQL job, Kubernetes will actually automatically delete all the things that Flink SQL job owns. And that'll actually cascade through multiple levels of operators if you needed to, and it just all happens automatically. Because the Flink deployment operator links ownership of the things that it produces back to the Flink job, Flink deployment, and so on. So long as all operators sort of participate in this pattern, you get all this for free, which is pretty nice. All right, so next level, automatic table registration. I think you probably saw this coming, right? All right, so the question is like, why do we have to write this, this DDL, create these tables in DDL? Why do we have to do this by hand? And I already mentioned that it's fragile, right? Like, it's not that hard to write, but once I write it, even if it's only in one spot, there's no guarantee that it's true forever, right? It might diverge from reality. And especially if you have something like Pinot, right? If you think about Pinot, it knows, of course, what tables exist in Pinot. It knows the schema of those tables. So why are we trying to like replicate that knowledge in a YAML file, right? Even if it is DDL. So you can imagine some sort of transformation that goes from Pinot into this Flink table. An alternative that I would recommend is to use a centralized metadata catalog, something like Data Hub. And the idea here is that you can have multiple sort of data plane systems or databases like Kafka and MySQL, Pinot, and they can integrate with Data Hub and register the schemas that they use, register the tables that they use. In Data Hub parlance, it's called data sets. And the idea here is if you're using Data Hub already, your Flink SQL job operator that you might be writing can just talk to Data Hub to figure out what tables there are, what schemas there are, instead of like talking directly to Kafka and MySQL and Pinot to do all these queries, because that could get complicated, right? So if we built such an operator, we sort of like extend our model. This means that we don't actually need the table YAML anymore. We could potentially just link, or sort of reference directly to data sets in something like Data Hub. And so now you can see the operator is starting to get pretty smart, right? You're pointing it at a Data Hub data set, and it has to go and talk to Data Hub, download schemas, like interrogate Data Hub to figure out what tables are there and that sort of thing. And then sort of like auto-generate the DDL on your behalf, right? But it's possible, right? And then, of course, now this is the sum total of what we have to write to create a new job. All right, so let's take the model even further. Level 4 is declarative infra. And this isn't super novel, but I'll show you why it's relevant to data pipelines. Okay, so there already exists data plane operators out there, especially like Kafka operators, and especially Kafka topic operators. But the idea here is you want to, or you can have a set of operators that just represent like physical tables or physical data sets or topics, whatever they are, in your databases in your data plane. So a Kafka topic operator, for example, would implement a Kafka topic custom resource and then go and create the physical Kafka topic in Kafka for you, right? So instead of talking to Kafka, you can talk to Kubernetes and say, hey, Kubernetes, I'd like to create a Kafka topic. And then the Kubernetes operator steps in and actually does that for you. And you can do the same thing with Pinot. And when I saw this the first time, and you're probably thinking the same thing, like, why? Like, why talk to Kubernetes when you can just talk to Kafka? Why talk to Kubernetes when you could talk to Pinot? And if you're a Pinot person, you probably like talking to Pinot. If you're a Kafka person, you probably like talking to Kafka, right? So like, why get Kubernetes in the mix? And the reason is like, especially in the domain of data pipelines, where we're intrinsically talking to a bunch of different systems, instead of talking directly to a bunch of different systems, Kubernetes can kind of be this like unified control plane for all of the different systems, right? So. And we do that by just implementing these operators, implementing these custom resources that represent things like tables and custom, and topics and so on. So this makes writing our like higher level operators much more palatable. Another reason why you would do this, another reason why you'd have things like a Kafka topic expressed in Kubernetes, is that you can have your custom resources reference each other in interesting ways. So, for example, on the left there, you can have a Kafka topic which, instead of knowing how to talk to a Kafka cluster, just references a Kafka cluster that you've already defined in another custom resource. So instead of like carrying around Bootstrap servers, for example, in your Kafka topic configuration, you just point it at a Kafka cluster that knows what Bootstrap servers is. So then you end up not seeing Bootstrap servers on everything. And likewise, like if you have a Pinot table that references a Kafka topic, then that Pinot table operator doesn't need to know how to talk to Kafka because it can, query Kubernetes for the Kafka topic, and it, it can then, find the Kafka cluster and get Bootstrap servers that way. So instead of like, copying and pasting all this the configuration everywhere, you could just have references to sort of like these, YAML resources in Kubernetes that define things once. Sort of the same idea I had with Flink tables, but expanded ad nauseum, right? And also you'll see ownership references come up again here. Notice that the Kafka topic is owned by the Pinot table. I'll show why that matters in a bit, but these are concepts native to Kubernetes. All right, so if you delete a Kafka topic, the expected, a Kafka topic custom resource, the expected outcome would be that the Kafka topic operator would go delete the Kafka topic for you. Now this can get kind of scary, right? If you're creating and deleting custom resources, you might be like dropping data from databases, right? And that can be kind of scary. So we'll talk about leveraging owner references to prevent that from happening. And that's our next bullet here, level 5. We'll talk about end-to-end ownership. So this introduces some high-level construct. We'll call it a pipeline. High-level operator, we'll call it the pipeline operator. And we'll introduce multiple owners of all of these things. So there's a lot of ways we could take this. This is just like, one sort of sketch. But you could imagine a pipeline YAML that basically is just a set of resources that the pipeline needs. So a pipeline custom resource might have a Kafka topic, might have a Pinot table, might have an Avro schema, and so on. And then ultimately, you have a little bit of SQL that implements the pipeline. So if you do this, the reason why you might do this is because the pipeline operator that implements this pipeline custom resource can go around taking ownership of all the things that you've referenced, right? So for example, we can implement a pipeline operator here. It listens for pipelines that are created and then looks in the pipeline to find all the resources that the pipeline references. And then the idea is that we would take ownership of all of the corresponding resources. So if I have a Kafka topic, I have a Pinot table, I have a schema, so on and so on, things that my pipeline might need. If they're all represented in Kubernetes as Kubernetes custom resources, then I can take ownership of those things by linking an owner reference from like the schema to a pipeline, right? Why would I do this? Well, there's a couple things, right? Now, if I delete the pipeline, I can automatically delete all the things that I deployed in response to that pipeline. But also, I can prevent other pipelines from accidentally deleting my Kafka topics. Like if I have, for example, multiple pipelines and they're all referencing the same Kafka topics, the same Pinot tables and that sort of thing, if you have multiple owner references for like, say, again, like maybe a Pinot table is owned by 2 pipelines, Kubernetes natively will enforce that it won't actively delete things that are owned by non-zero numbers of things, right? So if I have, if I delete one pipeline, we could set it up so that the Kafka topics that it references automatically get deleted because we don't need that anymore. But if there's another pipeline that does need it, then it will prevent it, right, from getting garbage collected in a sense. So now we've gone from, okay, we're using this owner reference concept and this custom resource concept to let us deploy things and let us undeploy things, right? And we're sort of like adding on this extra requirement that we don't want things to go away if they're used by multiple such owners, right? So we're actually preventing things from getting cleaned up using the same mechanism. And that's all I've got. Thank you for listening. Any questions?
Thanks for the talk. Is the Pinot table operator an open sourced thing?
Let's say a lot of these things exist in some form, but I don't know of an open source one currently. Yeah.
Got it. And the lineage of ownership that you just visualized, is that also propagated to the data hub?
That's a really good, like that's an insightful question. I would like that to happen. Yes, let's put it that way.
Okay, cool.
Yeah. So I mean, some of this stuff is pretty cutting edge, right? And like when we use the word lineage, and so in Data Hub, lineage is like where data comes from, right? Like this data in this database came from this other database, right? That's a similar model, but it's not exactly the owner relationship, but you could definitely imagine some correspondence there. And yes, the intersection between Data Hub lineage, or lineage in general, and data pipelines gets really interesting because it is the thing that moves things around, right? Yeah. Sorry, I don't have a better answer, but it's a really interesting question. Yeah, go for it.
Hey, so all the operators are completely kind of abstracted, right? So when a user defines his Flink SQL, say, and internally there is some resources that are allocated to the task managers on Flink, right? How do we control that? Like, let's say a user can define any SQL that he wants, and if the SQL kind of overwhelms the task managers, the application would slow down, right?
Sure.
Or the Flink cluster, the deployment itself would slow down. How do we control that? Because the user doesn't have control over what resources are allocated to the cluster, right? As we abstracted out all those things from the user,
right?
There's no way for them to control, say, hey, these are the resources that I need for my task manager or job manager.
Yeah, the model that I've seen successful is you basically layer in auto-scaling of some form, right? So you're right. If we abstract this to just SQL, right, then we lose the granularity of things like, well, how many tasks, how many cores, how much RAM, right? And so I think that's a really good call out. Like we need something more automatic in place to make that a viable solution, right? And yeah, it basically at big companies there are such things, but I think it's I think it's a solvable problem, right? To sort of auto scale Flink jobs. But yeah, I think that would be something, yeah, maybe for the next version of this talk.
Yeah, follow up, like would reactive mode in Flink help in this case?
I don't know much about that, honestly.
Okay.
Yeah.
No worries, thanks.
Yep.
Hey, thank you for the talk. Actually, if you want to, the previous person, if you want to know Flink, I can talk to you about it. I have a question about when you talk about changes happens outside the other infrastructure, right? Like if a user drop a column or change the schema. In this model, if the Flink job is already running and the Flink job is referencing to a column and that column is dropped, how does it handle that?
Yeah.
Do we wait for the job just fail itself, or is there like some more automatic thing to happen?
So that's one of the reasons why I like having like this, the data plane operator concept, or what I call that in the talk, right? Where like I define a Kafka topic in YAML first, and then that like reflect that into Kafka, right? Instead of the other way around, because then you can have like cascading updates. Like if I update a Kafka topic and like change its schema, for example, or change its partition count, Kubernetes can go around waking up all the operators that know about that, that resource and everything downstream of that resource. So like if you had a Kafka topic and you repartition it, say, that can wake up the Flink job or the Flink job operator and say like, hey, one of your resources changed, right? So unfortunately in Flink today, to my understanding, like you basically have to tear down the job and restart it with such things. I wish it were a little bit, more runtime configurable, but it actually only takes like a few seconds to deploy a Flink job with these operators. So like if you add a column to a table and then some things stop and then restart and it only takes a few seconds, that's actually a pretty good scenario. So I would say that you don't have to wait for the Flink jobs to error out before they die and then try to rebootstrap or reinitialize or whatever. I'd say that if you follow this model where your tables, your topics, and that sort of thing are actually defined in YAML, then you can propagate changes through the whole pipeline actively. Yeah, that's the dream anyway. yeah. Sorry.
Thank you for the talk. It was really awesome. One question about the Flink operator. Was that just a topic operator, just creating, or sorry, the Kafka operator is just creating topics, or does it require that Kafka stateful sets are running?
So it's interesting because a Kafka topic operator is a thing that exists today, but you usually see it in the context of a Kafka cluster operator. Like when you encounter operators in the Kubernetes world today, they're usually built around the idea of okay, I'm going to stand up a deployment of a Flink cluster or a Kafka cluster and do that work for you. And that same model works really well for things like Kafka topics, and in fact, it's super easy to write one. It's hard to operate a Kafka cluster, but it's easy to create a Kafka topic, right? So you would expect that to be the case with implementing a Kafka topic operator. It's easy to write a Kafka topic operator. You just take YAML and you go talk to Kafka and say, hey, this topic should exist, right? So those things exist, and it's a little bit weird because you don't usually see a standalone Kafka topic operator, and I wish that weren't the case, right? And I think this I think within your organization it's easy to define custom resources. I think it's easy to write these sort of like data plane operators that don't do anything other than create tables, create topics, and you can then leverage the hard work of the hard operators sort of underneath that, right? I haven't talked at all about managing the state of a Kafka cluster or a Flink cluster. Yeah, and those are the hard problems. Those are the complicated operators. Yeah, for sure. Sorry, go for it.
So in your declarative data pipeline, is there any way that you can help debugging the SQL, Flink SQL statement? Because one pain point is that you try to write those SQL statement by hand, and column names become mismatch, or date types will be become mismatch at some point. So do you plan to address that issue?
So two interesting things there. In the extreme case, when we move way down the spectrum in declarative mode, right? If you look at the SQL, it doesn't necessarily define columns. It doesn't select star from page view event, for example, doesn't make any reference to the data types or the columns involved. So that SQL can run in multiple different real world environments of what state the actual tables are. So that's one angle. And then also so in other words, I think the SQL's less likely to break if it doesn't have the DDL right there with it, right? If you've defined the DDL or you can auto-generate the DDL, then the SQL part is less likely to break as things change over time. The other thing is when you're, if your Flink job or whatever your workload is, right, if it encounters some errors, you can propagate those errors back upstream to the higher level resource, right? And so at the end of the day, what you want to see is my pipeline is running or it's failed because of this message, right? Here's the error. And that's not a really great way to debug SQL, but at least you get an overall pipeline state, right? So beyond that, you'd probably want to go dig into what actual jobs got created and look at the logs. Yeah, that's what I do currently. Yeah. I think we're short on time, but yeah, go for it. Yep. One more.
Right, thank you. So I think there may be another pipeline in LinkedIn. It's for batch, for more statistic data. So my question is, what do you think? Is there any plan for you guys to want to merge this two, or any plan for that stuff?
Yeah, I'll say that for another talk. I think the whole batch ecosystem, I think these same concepts can be applied. But yeah, it's early days there. Yeah. Cool. Well, thank you so much. Appreciate you listening.